These are the four kinematic equations, and they're fairly ubiquitous in physics, so it's good to know them. And it's also good to be able to know how to derive them for a couple of reasons. First of all, if you forget the equations on a physics test, you'll be able to rederive them there on the spot. And second of all, if you know how they're derived, you probably won't forget them in the first place. So let's look at the first one, and we start with the definition of acceleration, which is the change in velocity per change in time. We rewrite this as acceleration times change in time equals change in velocity. And we integrate both sides. The left-hand side we integrate from initial time to final time, which we just write as t, and the right-hand side from initial velocity to final velocity. The solution to this integral looks like this. Since acceleration is constant, we just multiply by t, and we would subtract 0 times acceleration. But I skipped that step. v1 minus v0, and we are left with the final velocity equals acceleration times time plus the initial velocity. And this makes sense if you think about it. If you start with a big velocity and you're not slowing down necessarily, you're going to end up with that's going to be added to your final velocity. And if your acceleration is really big, or if you accelerate for a very long time, those will both contribute to your final velocity. For the second equation, we start with the definition of velocity. Velocity equals the change in position per change in time. And we do the same thing we did with the previous problem. We multiply both sides by dt to get this guy. Here we denote our velocity as final velocity, v1, but this could really represent any velocity because this could represent any value of time. So what we're able to do here is take this value and plug it in to our velocity term here. We're going to switch the sides for convenience, and we'll rewrite this as acceleration times time plus the initial velocity times final time. That's what your change in x is equal to because we plugged in here. And again, we integrate both sides from our initial position to our final position and from our initial time to our final time. The solution to this integral looks a bit like this. Where v0 is just a constant. Here's our only variable, so that's the only place where we actually need to really think about our integration. We add our position to both sides. We'll just move it over here so I don't have to rewrite the whole thing. And that's this equation. And again, if you look at this, it makes sense. If you start off further down the track, your final position down the track is going to be longer. If you have a bigger initial velocity or you maintain that bigger initial velocity for a longer time, you'll end up further down the track. And it's the same thing with acceleration. If acceleration is bigger or the time accelerating is bigger, again, you end up further. And so those are the first two we're going to look at. For the third one, we look at this equation, and let's start with the definition of acceleration again. Change in velocity per change in time. Now, in all these problems, we have acceleration being constant, which means that if we were to plot time or velocity versus time, the acceleration would be the slope of this curve, and it would be constant, so the slope wouldn't be changing. So if we took an infinitesimal change in velocity per infinitesimal change in time, pretend that these lines are infinitely small, that would be the same as saying a big change in velocity over a big change in time. This ratio is the same because the slope doesn't change. So we can rewrite acceleration as delta v over delta t, which means that we can write it again as our final velocity minus our initial velocity. That's a big change in velocity over our time period, t minus t is naught, which is 0. So all we have to do is sub this equation into this equation. And that's how we get our third kinematic equation. So here I'm replacing A with what we know our A is, given a constant acceleration. In all these problems, acceleration is assumed to be constant. We can go ahead and rewrite this. To come up with this. We can combine these two terms. We have a positive whole v naught times t and a negative 1/2 v naught times t. 1 minus 1/2 equals 1/2. So I'm going to, again, just to save a little time, and what I just did there is I added these two terms. A whole minus a half equals a positive 1/2. And so we're left with the final term, a positive v naught, v1 plus v naught over 2 times time, because 1/2 and t are both common factors, plus initial position. That is our final position. So if you're given a problem where it doesn't show you acceleration explicitly, see if you have initial velocity and final velocity and see if you can solve it like that. The final one, this is the least intuitive of them all. Again, we start with the definition of acceleration, but we can rewrite this, and this is kind of a bit of a mathematical trick, as this, dv over dx, dx over dt. You'd see the x's would cancel out, and we would have dv over dt, the definition of acceleration. So this is valid, but instead of canceling out, we're going to keep this how it is, and recognize that this second part of the product, that's the term for velocity, change in position over change in time. So we have change in acceleration equals change in velocity over change in x times v. And we rewrite this, acceleration times change in x equals v dv. And again, we take the integral from initial position to final position, initial velocity to final velocity. The solution of the integral, it's going to look like this. Acceleration is just a constant here. So it's going to be d1 minus d naught. And I'm not going into a lot of detail on the integrals. I hope that's okay. And the second one, v is a variable, so you actually do have to think about the integral a little bit more. 1/2 v1 squared minus 1/2 v naught squared. Multiply both sides by 2. And here, I'm just going to rewrite this as delta x, our change in position. v1 squared minus v naught squared. We multiplied both sides by 2. And finally, we are left with this guy. 2 times the acceleration times the change in position. And you'll notice this isn't exactly what's in the problem statement. The reason for that is this kinematic equation assumes that we start at a position of 0. So if you start at a position of 0 and it says that in the problem statement, just use this. If you don't start at 0, it's delta x. It's the change in position. And again, this one makes sense. Your final velocity is going to be equal to your initial velocity. It's going to be proportional. So if you start with a bigger initial velocity, you're going to end up with a bigger final velocity. Again, if you have a bigger acceleration, or if that acceleration occurred over a bigger distance, you're going to have a larger final velocity. This one's important to remember because you'll notice that time is not included in any of the terms here. So if you don't see time in your problem statement, this would be a good one to remember. So in the next couple of videos, we'll go over some examples and hopefully build up your confidence in using these kinematic equations. Thanks for watching.